Today we'll be presenting phase 3 of the Flying Gecko. Our team was tasked with creating an inspection device that can replace people going into confined spaces of aircraft. So our drone that we created is 15 inches by 15 inches by 15 inches, which is small enough to be placed inside the access hole of a fuel tank and other applications like in the oil and gas industry and oil rigs or refineries. It's 7.1 pounds, which is light enough to be carried around by one person. The flight time is just a little over 20 minutes, which should allow for plenty of inspections. The materials were selected because of their lightweight properties and high strength properties, which are relatively common in drone and aviation applications. Also, their max temperature is well under what we are expecting in any of these applications. Also, the brushless motors will allow for operation in hazardous conditions that say may have residual fuel fumes in. And so the subsystem was divided up into 5 major components. First, we have the frame, which holds most of the weight. We have the front legs that are the main concern because they're the ones that are the first initial contact to the wall. We also have the blade guard and the main bolt pattern, which you can see here. We have the suction cup system. We have 4 suction cups on the 4 legs of the drone, and the kick box that allows for movement of the probe.
So for the frame, it is based on the Lumineer QAV 250, and it's been scaled slightly larger than the stock model to accommodate a larger payload. The frame will support all the other components. The motors, electronics, and other key components will be fitted in this middle section on the bottom and upper racks here, and the motors, legs, and blade guards will be mounted in these positions on the end of the arms. The testing kits will be attached by a bolt pattern to the underside of the frame here. The material of the frame is G10, which is a high-pressure fiberglass laminate. It was selected due to its creep resistance up to 130 degrees Celsius, and its properties are unaffected by moisture. It has a tensile strength of 38 kPSI, and then everything else is made of G10 except for these uprights and the screws that hold them in, which are made of aluminum. The arms will face stress due to repeated takeoffs and landings, and this means they could fail due to fatigue and bending. And on analysis, the arms have for static loading, they have a factor of safety of almost 30 and a fatigue factor of safety of 548. For the connection of the kits, that is a 4-bolt pattern on the underside of the frame, and it will face tension during flight and shear when the drone is in a vertical position on the wall. It could also face fatigue from repeated operations, and on analysis it had a factor of safety and tension of 1.33, almost 50 in shear, and a factor of safety of 72.38 in fatigue. These extremely high factors of safety mean that the frame is possibly over-designed, and it could be redesigned to reduce the weight of the drone, but doing so would provide minimal benefit as the redesign would likely be costly and time-consuming, and the weight is not a major constraint on the drone, so there would be minimal.
So for the front legs, we used a finite element method to allocate the maximum stresses over the geometries. So those were here just right at the joint, and these stresses were significantly smaller than the material due to stress. Then for the actuators, it was done a calculation for fatigue, where the design factor was 2, but with the calculations it was allocated a factor of safety of 1.68. In this case, we said it's good as it's bigger than 1, so the front legs are good to go.
Our motors, legs, and blade guards are all connected to the frame by a pattern of 4 bolts. The 4 bolts are arranged in a square/circular orientation. The 4 bolts are all grade 1, size number 6, and they have, when combined, they have a factor of safety of 10.54 under worst case scenario loads. An additional plastic blade guard was designed to protect the blades from light contact with surfaces to help prevent crashing in confined spaces.
So for the suction system, we went ahead and used 4 30mm flat suction cups that are going to be attached at the base of each of the legs on the drone. These suction cups are going to be powered by 2 micro pneumatic pumps. One is going to be operating for the front 2 legs, the other one is going to be operating the back 2. And we're also going to be using 4mm hoses that are going to run through the leg of the drone, connecting the pumps to the suction cups, which will allow for a smaller and sleeker design profile.
So for the kit design, the purpose of the kit is to lower the probe right here down to the surface of the wall. The probe can move in a 7-inch by 3-inch box, allowing for multi-point or point-to-point inspections. There's also a shield that goes around this to keep the probe from getting dirty or any debris getting in there. So the components move like a claw machine. So the upper components, which you can see here and here, they allow for movement laterally. Then there is a smaller piece that runs along with it, and inside of it is a worm gear where a smaller cart moves back and forth, moving this way. And then the probe is placed on that little cart, and then a gear here moves it up and down. So most of the kit stress testing was done using SOLIDWORKS FEA program. All the solid bodies or rigid bodies were done using it that way. For all these pieces here, they had a factor of safety of over 8. The only area of concern we have is the bolt stress connecting the upper and lower frame, as it's carrying the weight of pretty much the whole kit as well as the conduit bag. So kind of for what's next, advanced fatigue calculations need to be performed on the sliding motion. We aren't too concerned about the alternating motion or alternating loads because of how low they are. This will need to be done using prototype testing. Also, we've been looking into maybe doing testing at the corners where they make a 90-degree angle. The probe has enough length to extend all the way down for us to do inspections like that. But if we were going to do that, the helix or the spur gear will need to be changed to a helical gear that moves the probe up and down. So finally, in conclusion, we did find some design corrections that need to be made. The biggest ones were the SOLIDWORKS model's bolt patterns not matching up. Because of the high factors in safety and how small off they were, we weren't too worried with the overall outcome of the stress testing. The main one is the bolt pattern that runs through the blade shield, the front legs, the main frame, and into the motor, and that would everything's just off just a tad bit. The other thing is the kit box, some of the bolts don't line up. We also have a little worry with the suction line kinking because of a harsh angle leading out of the legs. And one fix we could do that is just remove some of the material due to, again, high factor of safety. And then kind of next thing, we want to look into possible corner inspections. We don't think that would be too hard to do and would add a lot of value to our drone. Rapid prototyping can be done because of the high factors of safety. We can 3D print this using ABS plastic and should still get a good idea of how it functions. And then also because of how small the components are, we need to look into manufacturing constraints.